The learning objective for this podcast is to identify different types of bonding and to learn about the nature of these bondings. So the four different type of bondings that we're going to discuss in this podcast are ionic, covalent, covalent network, and metallic bonding. So first of all, bonding, as we commonly call it, refers to interatomic or intramolecular bonding, and it's important to identify this or separate this or contrast it to intermolecular bonding. Intramolecular bonding is what brings the atoms or ions together to form one unit, like a molecule or a formula unit for an ionic compound, as opposed to intermolecular bonding, where the already formed molecules further attract each other, or already formed formula units further exhibit forces of attraction via intermolecular forces. So this podcast focus is on interatomic or intramolecular bonding. There are four types of bonding: intramolecular bonding, ionic bond, covalent bond, metallic bond, and covalent network bond. Ionic bond is a term given to the electrostatic attraction between oppositely charged ions. So ionic bond is always between a metal and either a non-metal or a polyatomic ion. So ionic bond is characterized by presence of a metal in it. For example, NaCl, you'll know, is ionically bonded because it's got metal sodium in it. KCl will be another example of ionic bonding because there is a metal potassium in it. Ionic bond is formed by transfer of electrons. So the metal gets rid of its electron, forming a cation. The non-metal or the polyatomic ion accepts these electrons, forming an anion, and because cations and anions have opposite charges, they electrostatically attract each other, and this electrostatic force of attraction is called ionic bond. Ionically bonded substances generally are present as solids. Covalent bonding, on the other hand, is formed by sharing of electrons between two atoms, so there is no transfer. The atoms will share electrons between them, and this occurs generally between non-metals. There is no metal present. For example, carbon dioxide, P2O5, NO2, etc., etc. When there is no metal present, we call it as covalent bonding, and generally there's sharing of electron that's happening between them. And covalently bonded substances are generally present as liquids or gases. There are covalently bonded solids as well, like ice is one example, but general state of covalently bonded substances is liquid or gases. The next type of interatomic or intramolecular bonding is metallic bonding, and metallic bonding is what's present in pure metals and metal alloys, and this is based on sea of electron, and we will be going in detail over these kind of bondings in further slides. So I'll just give a brief introduction. Here there are a lot of free electrons that roam about in a positive sea of nuclei. So the nuclei, the individual nuclei, do not hold on to their electrons very strongly, so the electrons have freedom of movement, which we call as free electrons, and this model is called electron sea model. The last type of bonding is covalent network bonding, and this is, you are all familiar with the term network with the computers. You know, when a number of computers are bonded together, we call it a computer network. Similarly, when there are a bunch of atoms or a bunch of molecules that are bonded together via covalent bonds, forming like a macromolecule, we call it covalent network bonding, and we will be looking in detail each of these bondings in the future slides. So if we were if we were to compare the strength of bonding on a continuum of electronegativities, you can say that from covalent to ionic, there is a larger difference in electronegativity. And at some point, the electronegativity difference between atoms becomes so much that sharing is just not possible, and hence transfer occurs. So you can almost think of ionic bonding as extreme case of covalent bonding, when the difference in electronegativity is so large that there's no sharing but only transfer. Now let's take a closer look at each of these type of bondings. First of all, ionic bonding. The basic thing to remember here, it's always present between a metal and a non-metal. And this doesn't have to be a non-metal, it could be a polyatomic ion as well. And an example of this polyatomic ion could be Na3PO4. This will be ionic bonding, just like NaCl would be ionic bonding. Ionic bonding forms when an atom, generally the metal, loses electrons to form a cation, and an atom, generally a non-metal, accepts these electrons to form an anion, and now there is electrostatic attraction between these cations and anions, and we call it as ionic bonding. The question is, why does ionic bonding happen? Because the bonded formula unit is more stable or lower in energy as compared to the ions. So there should be a lowering of energy for ionic bonding, or any bonding in chemistry to happen. Generally there is lowering of energy. Now, electrostatic attraction results because of the opposite charges. So first the charged ions are formed, and then there is electrostatic attraction between them. And ionic bonding happens when the electronegativity difference is greater than 1.7. And the maximum electronegativity difference is 3.3, which is for cesium fluoride. Other thing to know about ionic bonding is, as a result of ionic bonding, generally solids are formed. And the last important thing is, these solids are not present randomly, but they are present in a crystal structure. Crystals are repeating patterns of structure, like NaCl is a crystal structure, and each Na is surrounded by a certain number of Cl- ions, and this structure is repeated throughout. Lastly, and most importantly, what do we call the unit of ionic bonding? The unit of ionic bonding is called formula unit and not molecule. Some people erroneously call formula unit as molecule. It's wrong. NaCl is not a molecule. NaCl is a formula unit. And how do we write Lewis structure for ionic compounds? For writing Lewis structure for ionic compounds, you write sodium and you write how many valence electrons it has. Well, sodium ion has no valence electrons, right? Because it had one valence electron that it transferred to chlorine to form chloride ion. So chloride had 7 electrons, and I can draw the 8th electron with a different color so you can see that. And this leads to a -1 charge for chloride, and now there's electrostatic attraction between them. I mean, you obviously don't see these lines, I'm just drawing it to emphasize that there's electrostatic attraction, and that attraction is called as ionic bonding. So to write the Lewis structure, you use brackets to show Lewis structure of an ionic compound. A quick understanding check at this point. Could you write Lewis structure for calcium sulfide? Take a moment. If you get it right, it should look somewhat like this. With a 2- charge. Moving on. These are a couple of animations. I would recommend that you go watch them so you have a visual of how the lattice actually look. Then moving on to the next type of bonding, which is covalent. But before we go there, let's talk about strength of ionic bonding. So how strong is an ionic bond is determined by something called as lattice energy. Lattice energy is the measurement of energy of stabilization, and technically The technical definition of lattice energy is its amount of energy required to completely separate 1 mole of solid ionic compound into its gaseous ions. And these states are very important to remember. So if we were talking about lattice energy of NaCl, so we take 1 mole of solid NaCl and we see how much energy is required to break it into 1 mole of Na plus and 1 mole of Cl minus ions in their gaseous state. And whatever energy is required here is called lattice energy. And to measure lattice energy, the formula that's used is lattice energy is directly proportional to the product of the cation charge and anion charge divided by the distance between the nucleus of cation to the nucleus of anion. So the larger the atomic radius, the smaller would be lattice energy, because greater the distance between the nuclei of the two ions. The greater the charges between the cation and anion, the larger the lattice energy. Again, this is a great animation to go here and to see. This animation shows you how a lattice is formed, and this further tells you the definition of lattice energy. You can write it either backwards or forwards. Its amount of energy released when 1 mole of solid compound is formed from its ion, or you can talk about it in terms of breaking 1 mole of a solid compound. Both are the same, just their signs are opposite. And here this is a little animation to see lattice energy, how this forms. If you hit play here, there's a cation and anion. They go and attract each other. This transfer of electrons. So you can see cation and anion have already formed. And each cation gets surrounded by anions. And now the cation further builds up, comes to the side, and hence a lattice structure is formed. And to form 1 mole of solid ionic compound from 1 mole of gaseous ions, whatever enthalpy or energy change happens, we call that as lattice energy. Now back to the PowerPoint. So this is again a quick understanding check for you. Figure out between NaCl and KCl which one has a greater lattice energy. So you know that Cl is common in both, so its charge or size doesn't matter. Sodium and potassium both have +1 charge, so really ultimately you're looking at the size. Since the size of potassium ion is much bigger than the size of sodium ion, KCl will have a lower lattice energy than NaCl. So the greater lattice energy will be NaCl. Here the greater lattice energy will be MgS, because Mg and S both have 2 charge as compared to 1 and 1 charge. Even though there's size difference, but charge difference overcomes that. So we'll say that MgS has a greater energy as compared to NaCl. Moving on finally to covalent bonding. Covalent bonding is done by sharing of electrons. And how electrons are shared, evenly or unevenly, further leads to 3 types of covalent bonding. So covalent bondings could be non-polar covalent, that is the first type. Second type of bonding, covalent bonding, is polar covalent or PC, and the third type is coordinate covalent. And I will go over each of these in detail in a minute. So covalent bonds are formed by sharing of electrons, and ultimately why do atoms decide to share their electrons? Because they want to be in lower energy, and hence they are more stable. Covalent bonds are formed when the electronegativity difference is equal to or less than 1.7, because remember, greater than 1.7 tends to form ionic bonds. If electronegativity difference is between 0.3 to 1.7, then it forms a polar covalent bond, where between 2 atoms, atom A and atom B, electrons are shared unevenly. They are still shared, but if B has a greater electronegativity than A, B tends to pull the shared electrons more towards itself, acquiring a little negative charge, while the electrons stay a little farther away from A, even though they are still shared by A, acquiring a little positive charge. And a polar covalent leads to molecules which are called as dipoles. I'll write it over here. Dipoles, because these molecules seem to have 2 ends, dipoles. We'll call this molecule a dipole because it has a positive and a negative end. The second type of bond is nonpolar covalent bond. Generally, nonpolar covalent bond is formed between same atoms, like when a chlorine molecule Cl2 is formed by two chlorine atoms, a nonpolar covalent bond is formed, or when hydrogen molecule is formed by sharing of electron by two hydrogen atom, a nonpolar covalent bond is formed. Here electronegativity difference is between 0 and 0.3, very little. Now what is a coordinate covalent bond? A coordinate covalent bond generally is present in Lewis acids and bases, and we'll be going over it a little later in the year. In Lewis acids and bases, a pair of electron is shared between the two atoms or participating species, but this shared pair is provided by only one of the species. So maybe B has a complete octet and B shares two of those electrons in the middle. A shares B's electron but does not provide any electrons to be shared in the middle. Such bonding is called coordinate covalent bonding. Now, strength of covalent bonding is determined by electronegativity difference. So the higher the electronegativity difference, the weaker the bond is. If it is a nonpolar covalent bond, it's stronger than a polar covalent bond because electrons are evenly shared. Now this is a chlorine molecule and it shows how the electron cloud is shared of each atom. The electron cloud of each atom is shared and electrons move in that cloud between the nuclei of two atoms. These are good visuals for you to have because it's hard to visualize these 3D structures in your head. The next type of bonding is called metallic bonding, and metals have a very special structure which we call as electron C model. Pure metals, aluminum foil, lead, silver, gold, all of these exhibit metallic bonding. What's so special about metallic bonding is what you see here is they're a bunch of positively charged nuclei, but they don't hold on to their electrons very tightly. So these electrons are free to move about. If this electron is present here, it is attracted by this nucleus. But if it goes here, it might be attracted by this nucleus. And if it goes here, it might be attracted by this nucleus. So as a result, what happens, this overlap of d orbitals, so electrons can move between the orbitals without actually breaking bonds. Hence the metals are malleable, or they can be hammered into sheets or stretched into wires. The other thing about free electrons is because these electrons are free to move about, they can conduct electricity, and hence metals are good conductors of electricity. And you can see that this bond between the nucleus and the electrons not very strong. The electrons are free to roam about. Hence, metals have low ionization energy and low melting points. You can melt them easily. Now, this is a nice visual to show you how electricity is conducted. So, we all know that metals are good conductors of electricity. So if we apply electric field to it, electrons move from negative to carrying the negative charge with them to the positive end. Hence, metals are always good conductor of electricity. And due to these free electrons, metals are also good conductors of heat. Lastly, metals are ductile and malleable because of the overlap of d orbital. The layers of metal atoms can easily be stretched without really breaking the bonds. Hence, you can stretch the metals into thin sheets or wires without breaking them. The last type of intermolecular bond is called covalent network bond. And network is big network of molecules or atoms that are connected through covalent bonds. Covalent network always result into solids. as were metallic bonds. So these covalent network solids they have very high melting point, very high boiling point, and they are generally insoluble because you can see that each atom or molecule is bonded to other through a covalent bond. And covalent bonds are very strong because they are formed by sharing of electron and not transfer of electron. So covalent bonds are very, very strong. Now this is structure of diamond and graphite, and at this point I'd like to point out that diamond and graphite are called as allotropes of each other. Allotropes are substances that have different properties but are made of entirely same element. So graphite is made up of carbon atoms only, so is diamond, but they have totally different properties. Graphite is the pencil lead and diamond, you know, is a precious stone. The difference between the two is in the way they are bonded. In graphite, there are layers of carbon atom that are covalently bonded, but between these layers there are only weak intermolecular forces happening. So these layers are free to slip past each other. So as you write with the pencil, these layers can separate out and deposit on paper in the way you move the pencil, and hence your writing happens. Diamond, on the other hand, due to direct covalent bonds between each atoms, is very hard to break and is very stable. The common examples of covalent network solids, and I would suggest that you should memorize it, are diamond and graphite, silica, which is also called quartz, germanium, silicon, silicon carbide, and boron nitride. And I will end this podcast here. We will go over octet rule and Lewis structures in the next podcast. Thank you for listening.